An oxidation state is a number that is assigned to every atom in a molecule. Every atom has one. In this way, oxidation states are much like formal charges with one key difference. Recall that in assigning formal charges, the ownership of the bonding electrons was split evenly. Take, for example, carbon dioxide. Based on location on the periodic table, we expect the oxygen atoms to own 6 electrons and the carbon atom to own 4. If we say that in each double bond, 2 electrons belong to oxygen and 2 electrons belong to carbon, then the oxygens do own 6 electrons in their octet. And carbon owns 4 of the 8 electrons around it. No formal charges. This assumes that the bonds are purely covalent. But what if we assume that the bonds are ionic? That is the situation when assigning oxidation states. Instead of having each atom own 2 of the 4 electrons in the double bond, what if the more electronegative atom, in this case oxygen, owned all 4? Then each oxygen atom owns 8, and carbon owns none. That gives an oxidation state of -2 for each oxygen and +4 for carbon. Of course, we know that bonds like the CO double bond have some degree of covalent character and some degree of ionic character. So the real situation is what we called partial charges. Carbon doesn't have 0 charge, but it won't have a +4 charge either. It will have some positive charge. Likewise, oxygen is neither 0 nor -2, but it does have some negative charge. You might ask, do we need to draw Lewis structures every time we want to determine oxidation states? Fortunately, no. There are some shortcut rules that you need to know that are useful in assigning oxidation states. First, elements, when by themselves, have an oxidation state of 0. Second, since this is based on the more electronegative element owning the shared electrons, fluorine, the most electronegative element, will have an oxidation state of -1, except when it's by itself, where its oxidation state will be 0. Notice that these rules are in order of priority. Third, if you have a monoatomic ion, the oxidation state will be the same as its charge. Fourth, hydrogen will have an oxidation state of +1 when it's in a compound. Fifth, oxygen will have an oxidation state of -2. Notice that we have only mentioned 3 elements: fluorine, hydrogen, and oxygen. Everything else we will have to figure out by deduction, knowing that the sum of the oxidation states of all the atoms must equal the overall charge of that chemical species. Note that this is the same rule as we had with formal charges. Let's see how this works with some examples. First, H2. We recognize H2 as an element. We see by rule number 1 that the oxidation states of elements are 0. So each hydrogen atom in H2 has an oxidation state of 0. And we'll write it twice to emphasize that point. The next example is CuCl2. Though we don't have rules for copper or chlorine, we should recognize this as an ionic compound composed of monoatomic ions. So we can use rule number 3 to help us. We know that the charge on a chloride ion is -1, so that is their oxidation states. Since there are 2 of them, the charge on the copper ion must be +2. So, being a monoatomic ion, its oxidation state is also +2. Our third example is CH3F. We see that we have a rule for both fluorine and hydrogen. We can assign an oxidation state of -1 to fluorine and +1 to each of the hydrogens. We'll write +1 3 times. Notice if we add those numbers up, they come to +2. We know by Rule 6 that all of the oxidation states must equal the overall charge, which on this compound is 0. Therefore, carbon must have an oxidation state of -2. Our last example is the sulfite ion, SO3 with a 2- charge. We don't have a rule for sulfur, but rule number 5 says that the oxidation states of the oxygen atoms are each minus 2. These add up to minus 6. In this example, the oxidation states have to equal minus 2. This means that sulfur has an oxidation state of plus 4. By the way, you might notice that when we write the oxidation states, we write the sign first, then the number, to distinguish oxidation state from charge, where we write number then sign. These rules are easy to learn if you work some more practice examples, but it's very important that you do so. Being able to assign oxidation states is essential in identifying and manipulating oxidation-reduction reactions.